Hi YouTube, my name's Jeff and I'm the VogMan. Last week I shared part 1 of my electric Foundry build with you, and as promised, here's part 2. If you haven't seen part 1, there's a link appearing on the page right now, and that's really the place to start. If the link hasn't appeared, try the description below. Otherwise, let's crack on. It was around this point in the build that I noticed the mortar had a significant strengthening effect on the bricks. In this scrap heats test, you can see how easy it is to damage untreated bricks, but those with even a very thin coating of mortar do seem much stronger. This made me rethink the top of my Foundry, which is likely to receive a lot of wear and tear. I removed the top frame, added water to some mortar, mixed this to the consistency of runny paint, grabbed a brush and started painting the top. I was so pleased with this that I extended it down a couple of rows inside the Foundry, making sure I didn't accidentally coat any coils. I added 2 coats in total and I let this dry a couple of days. I still had 4 bricks left from my original 30 and I decided to bond 3 of these on edge to make a nice thick lid. Here's 2 of them, and you can see I've recessed out the ends a little to make room for an inch square piece of frame. I bonded these with mortar and left them 24 hours for good measure. The following day I stretched more thin polythene across the top and then I pushed home the metal frame. I scraped a thin coating of mortar across the bottom of these 3 bricks and positioned them nice and centrally. These comfortably covered the main chamber of the Foundry. But as I looked at this, I looked at my collection of offcuts and began to ponder. The offcuts were perfectly shaped to retain the hexagonal pattern, so I couldn't resist bonding these on. And I kinda got carried away with this. I guess I was having too much fun. It looks a bit of a crazy mess, but the idea is to add more insulation and integrity to the lid. In bricklayer fashion, I staggered joints to add strength, and then I added a thin paint coat of mortar. Then I sliced a brick in 2 and added these 2 slices to finish off my supply of 30. Okay, the finished look is a little unorthodox, and any comments about looking like a face will be ignored by me and my mate Dave the Lid. When I was happy the lid had had enough time to dry, I pushed through some lengths of box steel. At the end of these I'd already drilled a 10mm hole. Rather than try to calculate exact lengths, I slid some overly long lengths of box steel onto some threaded rod. Some simple maths told me that 5 inches would be long enough to fit this gap neatly, so I placed this onto the upper frame at the rear corner. Pulling everything back through, I was able to gauge where everything would comfortably rest. This enabled me to cut those dangling lengths to something more suitable and weld together this basic H support bracket. The threaded rod was pushed back in place and I used nuts and washers to ensure everything was aligning nice and centrally. Careful use of a tape measure was a must. The H bracket could then be welded to the frame. On the other side of the lid, I was able to adjust how long I wanted the handle to be. I cut this to a length that suited me and welded in a crosspiece, making sure I had plenty of clearance for gloved fingers. Notice these holes? I've drilled and threaded these to receive bolts, but I needed to make some simple brackets first. These hold and support the lid and the handles. I fitted these with bolts and metal putty, initially scoring position, then drilling, and finally adding some bolts with the putty. I made and fitted similar brackets at the back, and the whole lid pivots nicely, providing a nice big opening. With the lid completed, I turned my attention to the electrics. These connection points will be live when the Foundry is in use, and they need covering to prevent electric shock. These metal electric back boxes were a perfect ready-made solution. If I hadn't had these, I'd have probably built something similar out of sheet steel. These must cover the connection points, but not touch them. I enlarged one of the holes in the back of these boxes to take a rubber grommet. This grommet holds very snugly a 3-core heavy-duty mains cable. The grommet is necessary to prevent rubbing on the very thin metal box, which could easily slice into the wires. The colour of the wires isn't all that important in this instance. Polarity isn't an issue where there's a coil. However, I've stuck with the UK colour coding system for convenience. What is important is that the wires can safely handle the current that the Foundry will take. To each of these wires I've added more heat sleeving, insulating for electricity and heat. Ring connectors are firmly crimped in place. Notice the yellow tape on the rear cable. It's crucial to earth or ground all the metal involved for electrical safety, and this marked cable is the designated earth lead. Through the other small hole I placed a small bolt. To this I attached the earth ring connector. When it came to ring connectors, I didn't have one large enough to slide over the 10mm threaded bar, so I took a washer, drilled a small hole into it and made one of my own. The earthing cable is daisy chain connected to the second metal box and then onto the homemade ring connector. There's nothing inside the second box, its only function is to cover the connection points, but it still needs earthing. Over at the Foundry, the large homemade ring connector slides onto a threaded bar. As this is in contact with all the metal framework, this grounds everything nicely, including the handle. The other two ring connectors attach to the coil bolts. These are the positive and negative supply, though again polarity isn't important here. I also screwed in the thermocouple, and hand tight and a quarter turn with a spanner is snug enough. It was then just a question of fixing the boxes in place. I used the same bolt and putty approach for this, and it worked a treat, which finishes off the electrics on the Foundry itself. I now had to concentrate on persuading the Foundry to lift vertically, and to start this I cut 4 lengths of 1-inch square steel tubing and drilled some 6mm holes into them. Using some corresponding bolts, I was able to bolt together 2 side supports. These, when fitted, should sit vertically between the 2 remaining brackets on the upper and lower frames. Using some flat bar steel, I made 8 L brackets. Now you could buy something like this off the shelf, but I was looking for something sturdy, plus I still needed the welding practice. With a vice clamped onto my drill press and with some repeat positioning, it was possible to drill some consistently placed holes. When the L brackets and supports come together, they're ideally placed to accept a standard skateboard wheel. I found 8 washers either side of the wheel held it nice and centrally, and I placed 2 wheels on each support bracket. These wheel supports are now fitted and carefully aligned to be nice and level. Remember the L brackets for the wheels? If the top hole is elongated slightly, the bracket can pivot before being bolted down firmly. This is particularly helpful for vertical alignment. I then realised I'd left no connection points for the wire rope that was still to come, so I quickly fabricated and added these brackets. At this point I couldn't resist a temporary test. In fact, I hooked up the PID and ran the Foundry for a week at 100 degrees to help things dry off. I then finished off with a couple of hours at 800 degrees. It was over the course of this week that a few cracks appeared in the mortar joints. Heat didn't seem to escape, but it made me feel that mortaring the joints on the top 2 levels was pointless, but the choice is yours. Tao mentions in one of his videos that the outside of his Foundry reached over 100 degrees. I hadn't noticed anything like that on my short tests, but I didn't fancy losing that much heat. So in the interests of efficiency, I decided to wrap the outside with this insulation material. Now this claims to have none of the usual nasties associated with this type of product, but I wore a mask whilst cutting just in case. As a belt and braces kind of guy, I also decided to contain the insulation within a material sleeve, just in case any of the fibres decided to ignore the manufacturer's claims. This is fine cotton, the sort of thing your shirts are made from. It's strong and very tightly woven, so tight in fact that I've used it successfully to filter waste veg oil in the past. This meant getting out a needle and cotton, and I'm certainly no tailor, but it is functional. I will say at this point, if you're concerned about the cotton being at all flammable, I placed this piece in my kitchen oven at 150 degrees, which is 50 degrees more than Tao experienced. As you can see, it didn't burn. At the ends I looped some string and sewed this in place to help fixing. Remember, this is string and not cord. Cord is likely to melt. These insulation pads are certainly an added extra. They squeeze in nicely behind the threaded bar and cover everything except the metal boxes at the rear, which I want to be able to breathe and keep cool, and of course the 2 side wheel supports. Now remember how I didn't mortar between the top 2 rows? I didn't want them to get knocked off either, so I needed to keep them in place, but not to grip them too firmly or rigidly. Think of it a bit like holding a frog. You want to hold it tight so it doesn't get away, but not so tight as you end up with, well, frog soup. With this in mind, I made a crude jig from some brick scraps, and by welding some flat bar together, I made these simple corner supports. When it came to holding these in place, I initially positioned them with masking tape. I then took a long Jubilee clip and tightened this. Unfortunately, it was rubbish, it simply wouldn't tighten. So I ended up making my own version with metal strapping, angle iron scraps and a bolt. That worked much better. The strap was tightened such that it held the corner straps in place but didn't do so harshly. Just enough really. And that's the Foundry completely finished. What it now needs is a lifting mechanism, and that starts with timber. For these two uprights I went with 4x4s. This may seem a little excessive, but I want the wood to be strong and hopefully stay straight. They also need to be relatively tall to give lift clearance, and these were 1.8 metres or approximately 6 foot. To accommodate the roller skate wheels, it was necessary to cut a channel into one of the 4 sides on each post. This channel needs to be just a tiny bit wider than the wheel to prevent any binding, and roughly half an inch deep. Again, I turned to my router for this job. With that done, it's just a matter of fixing the posts in place. I initially used ratchet straps to hold the posts loosely in position, and then added top and side support until everything was rigid, level and complete. There's no fancy carpentry skills here, just cutting and screwing. The wheels need to rest within the channels of the posts. They shouldn't be tight against the frame, as some movement is expected. Ideally, they should float free of the posts, but look as though they're touching. That's how close we need them to be. But if they're fixed firmly against the post, you can expect a lot of jamming and no smooth lifting. Don't think of the wheel and channel arrangement as a restrictive frame. We want the Foundry to rise nice and straight, without twisting or turning, and hopefully without touching the posts at all. If the Foundry does need to strike the posts, the wheels should keep things fairly friction free and hopefully align things nicely on the way. To raise the Foundry, I toyed with a few ideas, including counterweights, a ratchet and chain system and a block and tackle. It was this last idea that really grabbed me. The pulley is an amazing machine, it's so simple and yet so effective. There's lots of informative material out there on pulleys, so I won't cover them in depth here, but a very brief review might be helpful. So, here's a heavy box that we need to lift. We've got to lift it upwards, and you can think of that red arrow as being the amount of weight and effort that's involved in the lift. So what if we use a pulley to help? Well, this arrangement, with a pulley fixed to a ceiling or stable structure, is called a fixed pulley. When the rope is pulled, the box can be lifted, but it still weighs the same. It's still the same amount of effort. Nothing has really changed. Yes, pulling downwards feels easier and more convenient than lifting upwards, but the only benefit of the fixed pulley system seems to be changing the direction of the effort. So a fixed pulley changes direction. But what happens if we take the pulley off the ceiling and put it onto the box? This setup is called a movable pulley, as the pulley moves whenever the weight is moved. One end of the rope is fixed to the ceiling and the other is pulled, and when the rope is pulled, the effort is halved. It's actually easier to lift. That's because half the weight is being shared by the ceiling and half the weight is being pulled by you. So a movable pulley reduces the effort, but of course we're back to pulling upwards in a direction that's not very comfortable. So let's add back in a fixed pulley on the ceiling. Now we benefit from both factors. The movable pulley reduces the effort and the fixed pulley changes the direction of the pull, making things nice and easy for us. The really great thing about this is that we can duplicate this many times over by adding more pulleys. Here's 6 in total. This setup dramatically reduces the amount of effort involved when lifting the box, in this case by a factor of 6. And that's the very setup I chose to use to lift my Foundry. Fortunately, rather than have all these separate pulleys and fixings, they can all be added together in what's commonly called a block and tackle. And if you're thinking all this sounds too good to be true and can't be right, you're correct, there has to be a payoff. And the payoff is you have to pull more rope. Whenever there's a block and tackle involved, you end up pulling far more rope than you normally would. But I think this is a fair trade. You can easily buy pulleys online, just make sure they're large enough to handle the size of the rope you use. I prefer the metal variety, and I also prefer slightly larger pulley wheels. Now I did conduct a few experiments, and the configuration I eventually came up with was this. It's difficult to show in place, but I'll describe it as best I can. It's important that both sides are pulled up at the same time to keep things nice and level, and I achieved this using a loop of wire rope connected to either side of the foundry. The steel rope ends pass around a thimble to produce a stable eye, and the rope is clamped with appropriate fittings. These then link to the appropriate brackets on the foundry. This loop of wire needs to feed through 4 pulleys, 2 singles and 2 doubles. Starting on the left, the wire rope goes up and over a single pulley, heading towards the right. It then rests on the top of a double pulley, through a hole in the frame, then over a second double pulley where it's directed downwards. It then does an 180-degree turn around a single pulley, goes back over the second double pulley, through the frame, over the first double again, and down the right side of the foundry where it connects. This whole arrangement serves only to redirect the direction of the pull, as I simply don't have the height available above my foundry. This second single pulley is floating. It's a movable pulley, and it helps centralise the pull on the cable. The whole weight of the foundry is now redirected to this pulley, to this exact point. It's now just a matter of using a block and tackle arrangement, but upside down from conventional setup. To lighten this load, I've used 2 triple pulleys in the block and tackle setup. The top triple pulley system is movable, and the bottom triple is fixed in place on the base of the frame. The lifting effort could be reduced even further with 4, 5 or 6 pulleys, but I could only find these triples and they did the job for me. To raise the pulley, this bottom rope has to be pulled upwards. It's actually not too bad. It's not easy, but it is easier than trying to lift the whole foundry by hand. At this point you could add counterweights to make lifting easier, or maybe a manual crank handle. You may prefer to lift the whole thing using an engine hoist, but as I'd gone this far, I wanted to finish things off with an electric hoist. If you've seen some of my other videos, you'll know I'm a fan of these electric wheelchair motors. They've got bags of power, have a fabulous gear setup, and are readily available used online. This one came with a bracket and a wheel. I was able to use the bracket as a guide to drill these square bar supports. This enabled me to screw the motor firmly to the frame. I originally thought of using the hub from the wheel to collect the rope, but the wheel was simply too large and the torque involved meant the wheel wouldn't turn. However, I was able to remove the centre from this hub and fashion a rope spindle that did work. But, and it's confession time here guys, it did get twisted out of shape. This shows you the forces that are involved here. This spindle was simply made from the hub, 4 lengths of M8 rod and an MDF stop end. But in use, the pressure of the pull squashed and bent the steel bars. Now I could have made another, but the squash centre actually makes the rope centre on the spool, so it's a happy accident, as the great Bob Ross used to say. So I've showed you what can happen, but the choice is yours. I decided to reinforce the bent rods with a few welds. I then taped over the threaded rod to reduce wear on the rope, and I also added a stop end to the hub, as once or twice the rope had spilled off this end. The spindle or spool is attached to the motor and the rope is firmly tied to it. Now hang on, I said rope there didn't I? Not steel rope, just rope. So what's the difference? Well, again, this is a personal choice. I found the steel rope very inflexible, but its close proximity to the foundry made steel an obvious choice. But for the pulling mechanism, this rope is much more flexible between the pulleys, and it's far enough away from the heat of the foundry not to be affected, so that's what I went with. To power the wheelchair motor, I used a 24 volt LED transformer. This one can handle 10 amps, so it'll have no trouble with the motor. When coupled with this momentary DP-DT switch, which can reverse polarity, I've got a motor that moves both forwards and backwards at the push of a button. I've already shared a video with you on wiring up a DP-DT switch to reverse polarity. It's a very useful switch function to know about. Now, where you place the motor is up to you. I placed mine on the opposite side of the frame to the pulleys, purely for personal convenience, but this meant I had to redirect the pull rope via 2 single pulleys up and over the Foundry, dropping down into the spool. And sure enough, this gutsy motor has no trouble lifting the Foundry. Its wonderful gearing system also ensures that when the switch is released, the Foundry is held mid-air, giving excellent access to the crucible. And once again, this video has gone on longer than I expected, so I think we're going to have to call that the end of part 2. But don't worry, part 3 is already on the cutting room floor, as they say, so it'll be with you in just a couple of days. In the meantime, I hope you enjoyed this instalment, and if you did, please like it. Please send in your comments and questions, and take a look at the other videos on my YouTube channel. If you haven't already, please subscribe. So that's it for now, guys. Look out for part 3, and thanks for watching.